Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples.
The equation has existed now for 51 years, and over those 51 years I've gotten many suggestions for additions to it, improvements, but in my view, and maybe I'm being protective, all of those things can be subsumed into the existing equation. What has happened is not a change in the equation, but a great improvement in the numbers that you put in it. It has 7 factors, so it means the accuracy of its result, which is a prediction of the number of detectable civilizations in the galaxy. The accuracy is dependent on the factor which is least well known. And unfortunately, that one, which is the longevity of civilizations in a detectable state, is still unknown and will be until we detect other civilizations. So we have that problem, that we still have one factor with a large error bar on it. But some of the others are really very well known, which they weren't 51 years ago.
Welcome back to Stories from Space. I'm your host, Matt Williams. And the recording you just heard was audio from an interview between famed astronomer and SETI researcher Dr. Frank Drake, considered to be the founder of SETI Science and the first president of the SETI Institute Board, and Andrew Franknoy of the SETI Institute, in 2012 as part of SETICon. This interview is an opportunity for Frank to explain how he got into astronomy in the first place, what drew him to the search for extraterrestrial intelligence, and how he came up with the Drake equation, which is arguably one of the best-known equations in the history of science. In addition, Frank reflected upon the legacy of the Drake equation and how it has held up over the last 50 years. Dr. Frank Drake passed away on September 2nd, 2022, at the age of 92. He's one of many luminaries who's died in recent years, including Stephen Hawking in 2018 and Freeman Dyson in 2020. And much like these colleagues of his, Dr. Frank Drake leaves behind an incredible legacy and will forever be remembered as the father of modern SETI. To break it down, the Drake equation originated from the first SETI meeting hosted by Frank Drake at the National Radio Astronomy Observatory in Green Bank, West Virginia in 1961. A year prior, Dr. Drake led what is considered to be the very first SETI project, known as Project Ozma. This survey relied on the Green Bank Observatory's 25-meter dish to monitor Epsilon Eridani and Tau Ceti, 2 nearby sun-like stars, between April and July of 1960. Specifically, the project scientists were monitoring these stars for radio transmissions that were close to 21 centimeters, coinciding with the wavelength emitted by cold neutral interstellar hydrogen. While the project was unsuccessful, it laid the groundwork for future radio surveys, and also piqued the interest of the scientific and SETI communities. In 1961, several noted scientists, including Carl Sagan, came to the observatory to discuss issues related to the search for intelligent life. In preparation for the meeting, Dr. Frank Drake prepared the equation that had come to bear his name, which effectively summarized the challenges for astronomers of finding evidence of intelligent life. As he later said, "As I planned the meeting, I realized a few days ahead of time we needed an agenda. So I wrote down all the things you needed to know to predict how hard it's going to be to detect extraterrestrial life. And looking at them, it became pretty evident that if you multiplied all these together, you got a number, n, which is the number of detectable civilizations in our galaxy. This was aimed at the radio search and not to search for primordial or primitive life forms." The formula that Drake produced essentially stated that the number of civilizations in the Milky Way galaxy that humanity might be able to communicate with at any given time could be derived by multiplying the average rate of star formation in our galaxy by the fraction of those stars that have planets, by the number of planets that can actually support life, by the number of planets that will develop life, followed by the number of planets that will develop intelligent life, those that will develop transmission technologies, and the final parameter, L, the length of time that these civilizations would have to transmit their signals to space. Over the years, the Drake equation has been subject to some criticism, largely because of the amount of uncertainty most of the parameters contain. However, this is largely the result of misunderstanding. The purpose of the equation was to encapsulate the challenges facing SETI astronomers by basically grouping all of the unknowns into one place. Essentially, Frank was saying that if we knew what the values were for all of these parameters, we could come up with an accurate estimate of how many civilizations there are. This was meant as a thought experiment more than anything. At the time of its formulation, only one of the parameters was not subject to uncertainty, which was the rate of star formation in our galaxy. According to modern estimates, there are between 200 and 400 billion stars within our galaxy, and astronomers estimate that there are between 1.5 and 3 new stars that form every year. In addition, the field of exoplanet studies has since exploded, with 5,514 exoplanets confirmed in 4,112 star systems, with another 9,820 candidates awaiting confirmation. From this, astronomers have deduced that the number of planets for every star system in the Milky Way galaxy is a non-zero value, which means that most, if not all, star systems have at least one planet. Furthermore, astronomers now estimate that those stars that have multiple planets will likely have 1 or 2 that lie within the circumsolar habitable zone, otherwise known as the Goldilocks zone, where liquid water can exist on the surface. Beyond that, however, the equation is still subject to a great deal of uncertainty. At present, scientists have no idea how many potentially habitable planets will actually produce life, nor can they even begin to estimate how many life-bearing planets will give rise to intelligent civilizations, or whether or not they would be dependent upon technologies that we would recognize. Nevertheless, this is one of the primary takeaways of Frank Drake's equation. When it comes right down to it, we have a very limited frame of reference. We know of only one planet where life is known to exist, Earth. We know of only one technologically dependent civilization, humanity. And in lieu of any evidence of intelligent civilizations out there, we are largely confined to making assumptions based on ourselves, and what we know to be physically possible. There is another major takeaway to the Drake equation, one which Frank may or may not have intended. Basically, even if one makes highly conservative estimates for each parameter, the numbers still turn out rather favorably. Even if we were to consider that for every habitable planet, only 1% will produce life, and only 1% of those will produce intelligent life, and only 1% of those will give rise to communication technologies that we could interpret and receive, the math still produces a handful of civilizations in our galaxy at any given time. However, the most significant part of the equation is arguably the L parameter, the length of time that civilizations will have to communicate with the outside universe. Frank Drake himself acknowledged this. According to Dr. Rebecca Charbonneau, a Karl Jansky Fellow at the National Radio Astronomy Observatory, who specializes in the history science, and who actually knew Frank Drake personally, Frank Drake considered L to be the most important parameter in his equation. In fact, according to Charbonneau, Dr. Frank Drake had custom-made plates on his card that read N equals L. In other words, the number of civilizations that exist in our galaxy all comes down to a civilization's longevity. Considering that Drake developed his equation in the midst of the Cold War, a time characterized by mounting tensions between 2 nuclear-armed superpowers, he and other SETI researchers were forced to consider that intelligent civilizations in our Milky Way might be subject to the same existential threats that we are. This includes, of course, the threat of nuclear annihilation. However, the 1960s also saw the rise of the environmentalist movement, where scientists were becoming increasingly alarmed at the rate at which human populations were growing and our collective impact on our natural environment. Here, too, SETI researchers began considering that intelligent life may be susceptible to self-destruction by outstripping its natural resources. This is perhaps the greatest legacy of the Drake equation, in that it focused attention on humanity's own rising sense of mortality. While the concept of civilization collapse is something that human beings have been contemplating since time immemorial, it was really only within the context of the 20th century that we began to contemplate the collapse of our civilization as a whole and possible extinction in the process. If, by extension, all intelligent civilizations have a life expectancy, where eventually their level of development will reach the point where they are the single greatest threat to themselves, this imposes some rather strict constraints on the Drake equation. But as we addressed in a previous episode, in addition to civilizations going extinct, there's also the possibility that they may be subject to exponential technological progress. This theory also emerged within the context of the 20th century, where it has become increasingly clear that technology is a very iterative process. With every major technological development, the time it takes to produce the next major development becomes that much shorter. Noted futurist Ray Kurzweil referred to this as the law of accelerating returns. If we extrapolate this for intelligent civilizations in our Milky Way, then we can also argue that L is not necessarily a function of mortality alone, but also a function of rapid development. This reveals another fact about SETI, which is that it has been largely confined to the search for radio technosignatures. This is entirely understandable considering our own history with radio technology and our continued reliance on it. However, that history has been relatively brief, and communication technologies are always evolving. In the near future, humanity may resort to optical transmissions, where information is beamed from place to place using lasers. Scientists are also beginning to consider that neutrinos may be a viable technosignature, as well as gravitational waves and gravitational lenses. This research has led to an expansion of what are considered viable technosignatures and things that SETI researchers should be looking for. Future surveys that look for spillover from optical transmissions or other advanced communication technologies that go beyond the radio spectrum may turn up evidence of multiple civilizations thriving in our Milky Way, thus demonstrating that the search for extraterrestrial intelligence was limited only by what turned out to be a narrow search parameter. Regardless, as Frank Drake himself acknowledged, we will not be able to address the uncertainties in the Drake equation or resolve the deeper questions it presents until we find evidence of other civilizations out there in the universe. In the meantime, the equation that bears his name has had a lasting influence. Alongside the Fermi paradox, the Kardashev scale, and the Great Filter hypothesis, it remains absolutely foundational to SETI research. To this day, scientists are still suggesting revisions for it, extensions of it, and are working hard to try and narrow down the level of uncertainty for each parameter. These efforts will be assisted by next-generation space telescopes, such as the James Webb Space Telescope, the Venerable Hubble, the Nancy Grace Roman Space Telescope, and the European Space Agency's Plato mission. These and ground-based observatories will greatly expand the number of confirmed exoplanets, will help to characterize their atmospheres, and narrow the search for life. This in turn will assist in narrowing the search for intelligent life by allowing us to discern potential technosignatures with greater ease. Machine learning will also play a major role, sorting through the massive volumes of data these observatories produce, and helping to discern patterns, which could indicate the presence of technological activity. On September 2nd, 2022, the world said goodbye to yet another famed and incredibly influential luminary. However, as long as the search for extraterrestrial intelligence exists, Frank Drake's legacy will live on. Tune in next week, where my guest will be Dr. Rebecca Charbonneau, as she regales us with personal stories of Frank Drake and her thoughts on his enduring legacy and major scientific contributions. Thank you for listening. I'm Matt Williams, and this has been Stories from Space.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.